The lift may last seconds. The preparation can take years. For 4 decades, a North Sea oil and gas platform supplied energy to homes and businesses across Europe. When that working life ended, the engineering challenge changed completely. A topside weighing roughly 25,000 tons had to be removed from its foundation in one piece and transported from open water to a recycling yard ashore. A single lift, 9 seconds, 25,000 tons of steel rising off the North Sea. Behind those 9 seconds, wells plugged, hydrocarbons drained, decades of marine growth stripped from legs no one had touched since the day they were driven into the seabed. The North Sea alone faces a decommissioning bill of around £24 billion over the next decade. What you are about to see is how engineers take apart the structures they were never supposed to remove.
The lift may last seconds. The preparation can take years. For 4 decades, a North Sea oil and gas platform supplied energy to homes and businesses across Europe. When that working life ended, the engineering challenge changed completely. A topside weighing roughly 25,000 tons had to be removed from its foundation in one piece and transported from open water to a recycling yard ashore.
Second, all personnel and operating systems were removed from the platform. Third, the topside itself was lifted away. Engineers chose not to dismantle the structure offshore. Instead, the entire upper platform was taken as a single unit and moved to shore for controlled disassembly. The actual lift lasted only 9 seconds. Behind those seconds were 2 years of preparation, a reduction in offshore work, and a plan to recycle more than 97% of the material brought ashore.
Before the same vessel set a world record on the Bravo, it had already broken one on the Delta. In 2017, the world's largest construction vessel moved into position around the 24,000-ton North Sea platform topside, ready to break the previous benchmark for an offshore lift in a single piece. The vessel's twin-hull design wrapped around the platform's 3 concrete legs, with dynamic positioning holding it inside a tolerance band measured in centimeters despite open sea conditions. Massive lifting beams extended from both sides of the slot and locked onto reinforced lifting points on the underside of the topside. Hydraulic motion compensation systems neutralized the wave-induced movement between vessel and platform, so the connection could be made as if the two were on dry land. The final cuts went through the concrete legs. When the fast lift fired, the entire 24,000-ton structure rose roughly 2 meters in seconds, separating cleanly from the concrete base before any wave could close the gap. The topside was sea-fastened on board and transported to the Able UK decommissioning yard in Teesside.
2 numbers explain why this lift mattered to the wider industry. 24,000 tons in one piece, 140 meters of water. The Brent Delta topside sat on a 3-legged gravity-based concrete structure standing in 140 meters of water in the Brent field roughly 186 kilometers off the northeast coast of Shetland. The figures that go with the lift vessel tell the rest of the picture. It is a dynamically positioned single-lift installation and decommissioning vessel with a topside single-lift capacity of up to 48,000 tons and a jacket single-lift capacity of up to 20,000 tons. The thinking behind the design is direct. Move the heaviest work off the open sea and onto shore, where the same job is safer and more cost-effective. After the 2017 lift, the topside was sea-fastened on board the vessel and transported to the Able UK yard in Teesside, where structural breakdown and recycling could be carried out alongside a quay rather than on a platform deck in the middle of the North Sea.
A vessel that can lift a whole platform out of the sea does not arrive overnight. It is itself a multi-year construction job. Time-lapse footage compresses the build into a few minutes. The port side half of the hull was assembled inside one dry dock in 2012. The starboard half was built concurrently in a second dry dock. Each half was floated out separately and then precisely brought together and joined in July 2013. The combined hull was moved between quays and into a further dry dock through late 2013 before officially leaving the shipyard in November 2014.
The vessel arrived in Rotterdam in January 2015, where the topside's lift system beams were installed between February and September of that year. The finished vessel is 382 meters long and 124 meters wide, with a bow slot 122 meters long and 59 meters wide for moving around a platform.
A platform at end of life is not just an empty frame on legs. Every system that ran for decades has to be unwound, one at a time. From the air, an offshore platform looks like a single steel object. Inside, it is a working industrial plant. Wellheads bring oil and gas from beneath the seabed up to the deck. Separators split the incoming stream into oil, gas, and water. A blowout preventer guards every well against runaway pressure. A central control room watches flow, pressure, and temperature in real time, with automatic alarms ready to trip safety valves and isolate equipment. Living quarters are housed in a block kept acoustically separate from the production area, with shift crews working 12-hour rotations. Supply vessels and helicopters keep the platform fed and crewed. None of that simply switches off on the last production day.
To understand why removal is hard, look at how a platform was put in place to begin with. A derrick lay vessel transports the jacket on a cargo barge to the field. Engineers prepare the structure on deck, then either lift it directly off the barge or release it down inclined launchways where it slides into the sea and floats on its own buoyancy. Controlled flooding upends the jacket from horizontal to vertical until it stands on the seabed. Long steel piles are then driven down through sleeves in the jacket legs by hydraulic offshore pile hammers, anchoring the structure to the seabed for the next 30 years. The topside, often weighing thousands of tons, is delivered separately on its own barge and lifted into position on top of the jacket by heavy crane. Bridges between modules and to adjacent platforms are then craned into place. Every one of these stages locks the platform into the sea in the seabed, and every one of them has to be reversed at end of life.
The topside is only half of what has to come out. Below it sits the jacket, the steel skeleton standing in the seabed, and that is its own removal job entirely. On the 21st of April 2022, the same vessel that had lifted topsides off the Brent field deployed its jacket lift system for the first commercial use, in 160 kilometers of water off the Shetland Islands. The lifted jacket weighed 8,100 tons, one of the heaviest offshore jacket lifts ever performed, and still well inside the system's 20,000-ton single-lift capacity. The system uses two connected 170-meter beams mounted at the vessel's stern. After the 8 jacket legs were cut underwater, the beams lifted the 85-meter structure clear of the water and tilted it back onto the main aft deck for transport. The jacket was then delivered to a deep-water port in the Shetlands, where the receiving yard targets 98% steel reuse.
Not every platform comes off in a single record-breaking lift. Most are smaller, older, and removed in campaigns. In the southern North Sea, a contractor took on the removal of 11 older gas platforms. Most of the work was preparation. The topsides were stripped and made safe long before the lift vessel arrived. Once the campaign began, 4 satellite platforms came out of the water in a short, tightly sequenced window. After hazardous material mapping, each structure was lifted and transported to shore for sorting, where 95% or more is recycled or reused.
Why can't engineers simply cut the platform and lift it away? Because under decades of marine growth, no one actually knows what the steel looks like anymore, and a structure that has not been read cannot be safely cut. Before any cutting tool can touch the legs, before any lifting point can be welded onto the deck, the surfaces have to be cleaned and the actual condition of the steel has to be read. Footage of a magnetic crawler working on a large FPSO, an oil tanker, shows the cleaning principle in action. A small support vessel is positioned alongside the larger hull, carrying the robot, the power cables, and the high-pressure water hoses on its deck. The M6 unit is checked over, then lowered into place, where powerful magnetic wheels lock it onto the steel plating. Above the waterline, the robot drives along the side, firing a high-pressure water jet that strips dense marine growth from the steel as it advances, leaving a clean strip behind on every pass. The unit then transitions across the waterline and continues working underwater on the submerged plating. The magnetic hold keeps it locked to the steel through the surge of the waves, and the cleaning continues on sections of hull no diver would want to inspect by hand. The pressurized jet dislodges marine growth without damaging the existing coating beneath. As the crawler advances, an onboard video camera and recording system run with it, and ultrasonic thickness testing is performed on the same pass, so the marine survey is conducted in parallel with the cleaning. Wall thickness, coating condition, and corrosion pattern all come back to engineers in the control room as real measurements. Operators monitor the surface quality on a live screen on the support vessel, replacing a diver next to a high-pressure jet with a person at a desk on deck. The same logic applies to a platform being prepared for removal. Decades of marine growth on the steel hide the very surfaces engineers need to read. Clean first, inspect on the same pass, document. Only then mark the cuts.
Ask any decommissioning engineer where the hardest cleaning job lives, and the answer is usually the same: the surfaces no human can reach safely. This magnetic crawler is designed for exactly that problem. The robot climbs vertical steel plating on the side of a large vessel, secured by a safety line from above and held against the steel by powerful magnetic wheels. A high-pressure water jet mounted at the front operates continuously as the crawler moves. Dirt, corrosion products, and marine growth are stripped from the surface without requiring workers to stand directly in the cleaning area. The difference is easy to see. Areas already covered by the crawler return to bare steel, while untouched sections remain coated with fouling. The machine is not limited to flat walls. It moves across curved hull sections, transitions around corners, and continues onto the underside of the structure. Even when operating upside down, the magnetic system maintains enough holding force to keep the robot attached while the cleaning head delivers consistent pressure. A technician controls the crawler remotely from a safe location, adjusting its direction and speed without exposure to high-pressure water or work-at-height hazards. Water and pressure are supplied continuously from a pump unit on the ground, allowing uninterrupted operation. The same principle appears in offshore applications. The crawler is shown cleaning the vertical columns of a marine structure, moving along large cylindrical members and removing marine growth in long, continuous passes. These are exactly the kinds of surfaces that become difficult, expensive, and potentially hazardous for divers to clean manually. That matters during preparation for removal. Offshore structures contain vertical legs, braces, underdecks, and other awkward areas that must often be inspected before cutting or lifting operations begin. Cleaning is not the final objective. It is the step that reveals the steel underneath. The process relies on high-pressure water rather than chemicals or aggressive mechanical scraping. The goal is to remove what covers the steel without damaging the structure itself. For difficult offshore surfaces, machines like this reduce worker exposure while making large-scale cleaning more predictable and efficient.
A 40-year-old jacket leg will not let you cut it carelessly. The same engineering that built the structure has to come back to take it apart. Once the surfaces are clean and the survey is complete, the preparation moves toward the cuts that will eventually free the platform from itself. Every cut changes how loads travel through the structure, which is why engineers plan the sequence long before any steel is touched. A portable CNC pipe cutting machine handles tubes up to 4,500 millimeters in diameter with wall thickness up to 120 millimeters, the actual scale of offshore jacket legs. The machine arrives on a truck and is lifted into the workshop by overhead crane, where the cutter beam is positioned against the large pipe and surrounded by scaffolding for safe operator access. A rotator with a speed controller turns the pipe under the cutting head. Drive chains are tightened around the body of the pipe, and overhead safety crane keeps the cutting structure balanced, and gas and power lines are connected to the cutter. The starting position and reference lines are laid out by laser. Before any flame touches steel, a dry run is performed, the cutter traversing the full programmed path with no torch on so the trajectory can be verified at full size. Only then does the engineer load the cutting program on the control computer, position the torch, and ignite the flame. The cut runs continuously around the circumference, sending sparks both inside and outside the pipe. After a complete pass, the cut section is freed and lifted clear by crane. The cut surface that is left shows the prepared bevels, K-bevels and X-bevels, and a finish smooth enough for high-quality weld joints, the same standard the original installer would have demanded. Most of the work takes place years before anyone sees the actual lift. A contractor running an 11-platform decommissioning campaign in the southern North Sea spent the preceding period preparing the topsides long before any heavy lift vessel arrived. Production was shut down, wells were plugged and abandoned, sealing the reservoir so hydrocarbons could no longer reach the surface. The process systems on each deck were flushed and purged, hydrocarbon residues inside pipes and tanks were cleaned out, and risers and pipelines linking the platform to the field were disconnected. Loose equipment was backloaded onto supply vessels and shipped to shore in advance. Structural engineers surveyed each deck, which had stood in salt air for decades, to confirm where the steel could still carry the new load path that a lift would impose on it. Reinforced lifting points, yokes, stools, and grillage were designed and installed onto structures never originally built to be picked up off their legs. Cuts through the jacket legs and supports were planned and pre-marked. Hazardous material mapping of the entire platform was carried out, identifying NORM, asbestos, mercury, chemical residues, and any other substance that would need controlled handling on shore. None of this work was visible from the surface, and none of it produced the dramatic footage of the eventual lift. But the contractor was clear about its importance. The reason the actual removal of 4 satellite platforms could run in a short, tightly sequenced window was that the engineering had been done in advance. The contractor described the campaign as one team across multiple specialisms, offshore engineers, onshore engineers, and operational crews, moving freely between land and sea so that every stage of the project was understood from both sides, with an open-door policy where issues were discussed directly and resolved on the spot. The same culture was credited with keeping the campaign free of accidents, injuries, or illnesses while it was running, with safety treated as a non-negotiable priority on every shift. After each platform was lifted and secured, a sea fastening procedure followed within 3 hours, and the vessel was ready to sail. The lifted platform was then transported to shore for sorting, where 95% or more of the material was recycled or reused, returning the field area back to nature. Every one of those numbers depended on the preparation. A platform that had not been cleaned, surveyed, isolated, and pre-cut would not have been ready for any of it. The visible lift is the moment everyone notices. The invisible work in the months and years before it is what makes the lift possible at all.
With the platform finally made safe, engineers face the decision that shapes the entire project. Should they cut it into smaller pieces offshore, or remove it in one massive lift and bring the hard dismantling work back to land? Before engineers choose a removal method, they need to understand what lifting equipment is available. A crane vessel does not automatically mean a single lift campaign. In many projects, heavy lift vessels are used to move modules that have already been separated from a platform. A lift beside a quay helps explain why modular removal became attractive for offshore projects. This operation involved a 600-ton module prepared for installation on an offshore production facility. The vessel approached the quay and completed a heavy lift using a long crane boom. Although the load was modest compared with the vessel's maximum capability, the sequence highlights a principle that also appears during platform removal. Large structures do not always need to be cut into countless small pieces. They can be divided into modules, prepared carefully, then transferred by specialized lifting assets. Within decommissioning projects, modular removal often sits between piecemeal removal and single lift removal. Engineers reduce offshore cutting by separating sections in advance while avoiding the extreme requirements associated with lifting an entire topside at once. A heavy lift vessel can then remove prepared modules and place them onto transportation assets for delivery to shore. The attraction is straightforward. Fewer offshore work hours can reduce exposure to weather delays and marine operations. At the same time, the project avoids dependence on a rare vessel designed for full topside removal. Every lift still requires planning, rigging design, weight control, and verification of load paths. The lesson from this transfer is simple. Successful removal often starts before the structure leaves the sea.
The biggest question is not only how heavy the platform is, it is where you want the danger to happen. Offshore in bad weather, or onshore in a controlled yard. A removal strategy begins before any cutting starts. Engineers first study weight, geometry, lifting points, transportation options, water depth, and the marine equipment available for the campaign. Those factors explain why some platforms are dismantled piece by piece, while others are separated into major modules, and why a limited number can be removed in a single lift. This topside loadout provides a useful example of the preparation required before a very large structure is moved. The processing topside weighed 28,171 tons and measured roughly 139 meters long, 69 meters wide, and 72 meters high. Before transportation, its weight had to be verified carefully. 64 load cells, each rated for 750 tons, were positioned above skid shoes so engineers could confirm the load distribution across the structure. That attention to weight is directly connected to decommissioning decisions. A piecemeal removal campaign may avoid the need for exceptional lifting capacity, but it increases offshore cutting, offshore lifting, and the total number of marine operations. Every additional task can be influenced by sea state, vessel scheduling, and weather windows.
Modular removal takes a different approach. Instead of cutting a platform into many small sections, engineers separate it into larger blocks that remain practical for transport and lifting. Heavy lift vessels, crane barges, and transport barges can then move those modules to shore. Offshore work is reduced while dismantling activities are shifted into a controlled yard environment. The loadout sequence shown here demonstrates why that approach can be attractive. The topside moved approximately 55 meters along skid tracks. Link beams created a continuous transfer path between the quay and the barge. Ballasting systems continuously adjusted the barge condition as weight transferred. Hydraulic arrangements accommodated movement while maintaining load control. The operation was monitored closely and guided by computerized systems that controlled each movement step. Every stage depended on precise coordination because even small imbalances could affect the transfer of such a massive structure.
Single lift removal pushes the concept even further. Instead of transporting several modules, the goal is to remove an entire topside or major structure in one operation. That can significantly reduce offshore exposure, but it demands extraordinary preparation. Engineers must understand structural behavior during lifting, verify load paths, define support locations, and ensure transportation arrangements are ready before the lift begins. Major projects illustrate the scale involved. One topside removed in a single lift weighed about 24,000 tons, while another project involved a 14,200-ton topside and an 8,500-ton jacket. Such campaigns require engineering, preparation, removal, transfer, transportation, and onshore disposal planning as one connected process. Another important consideration is where dismantling activities will occur. Cutting steel offshore requires crews, equipment, lifting support, inspection teams, and suitable weather. When larger sections are transported ashore, recycling, waste separation, and material handling can proceed with easier access and more predictable conditions. That advantage explains why operators often examine whether additional preparation before removal can reduce work at sea. The preferred solution changes from project to project because platform layouts and transportation constraints vary greatly overall today. The lesson is clear. Choosing between piecemeal removal, modular removal, and single lift removal depends on much more than mass alone. The decision combines safety, offshore exposure, available vessels, structural configuration, logistics, and cost. For the largest single lift projects, the answer depends on one of the strangest vessels ever built. A ship designed to slide around a platform, grab it, and lift an entire industrial plant out of the sea.
For the largest single lift projects, the answer depends on one of the strangest vessels ever built. A ship designed to slide around a platform, grab it, and lift an entire industrial plant out of the sea. Standing above the North Sea for decades, Brent Bravo reached the stage where production had ended and removal became the next task. The objective was not to dismantle the topside offshore piece by piece. The plan was to detach the entire upper structure and carry it to shore in one lift. That decision shifted much of the dismantling work away from an exposed marine environment and into a controlled recycling facility. Years of preparation were required because the platform had never been designed to be lifted from underneath. Engineers first reduced equipment, cleared unnecessary materials, installed dedicated lifting points,
and developed methods to separate the topside from its support structure while preserving stability. Lessons from an earlier removal campaign reduced offshore work and lowered exposure for crews. New approaches cut welding requirements and simplified preparations without reducing safety margins. The vessel selected for the operation approached with a split bow designed to surround the platform. Ballast systems adjusted draft while positioning systems held the ship within tight limits despite wind and waves. Several teams worked simultaneously. Vessel control, dynamic positioning, ballast management, and the topside's lift system had to operate as a single coordinated unit. The critical challenge was relative motion. The platform and vessel existed in an ocean that never stopped moving. Motion compensation technology allowed lifting components to connect beneath the topside while controlling movement between the floating vessel and the fixed structure. Accurate positioning was essential because contact with supporting legs during approach could create unacceptable risk.
Once lifting beams engaged the designated points, preparations entered their final phase. Separation work had already ensured the topside could be released at the planned moment. The operation then depended on load transfer. Weight had to move from the existing support structure onto the vessel rapidly and evenly. If one area accepted significantly more load than predicted, stresses could develop within an aging structure carrying thousands of tons. Then came the moment seen around the world. Roughly 25,000 tons were lifted in about 9 seconds. The speed was intentional. A fast lift reduced the opportunity for wave motion to create unwanted interactions between vessel and platform. What appeared simple from a distance represented the culmination of engineering analysis, structural assessment, marine operations, and precise timing. After separation, the mission continued. The topside had to be secured, transported, and delivered for dismantling and recycling. Yet the defining image remained those few seconds when years of planning converged into a controlled transfer of an immense load from a fixed offshore platform onto a moving vessel safely. Behind that short lift sat a sequence of decisions that began long before the vessel arrived. Wells had already been isolated, personnel removed, and the platform prepared for an unmanned condition. Every item left on board was reviewed because unnecessary weight could affect calculations. Engineers studied load paths throughout the structure to understand how forces would travel during separation and lifting. Weather also influenced planning. Acceptable operating windows depended on wave height, direction, and vessel response. The objective was not simply to find calm seas, but to ensure predicted motions remained within strict limits during engagement and load transfer. Simulations, procedures, and rehearsals helped crews prepare for conditions expected offshore. The operation demonstrated why large removals increasingly favor single-lift concepts when conditions allow. Fewer offshore construction activities can reduce exposure time at sea while concentrating dismantling work onshore. Brent Bravo therefore became more than a removal project. It showed how experience from earlier campaigns could be refined, turning lessons learned into a faster, more efficient method for handling one of the largest structures ever removed from an offshore field under demanding North Sea operating conditions.
Brent Bravo proved the speed of the lift, but an earlier operation showed how the concept reached full scale in the North Sea. Before a heavy offshore platform can be recycled, engineers must first solve a transfer problem. Tens of thousands of tons stand above a support structure fixed to the seabed. Waves move continuously around the installation. A vessel floats and responds to those waves. The challenge is to place the vessel beneath the topside, connect lifting equipment, separate the structure at the correct moment, and accept the load before relative motion creates damaging forces. The Brent Delta removal became one of the defining examples of that approach. The topside weighed roughly 24,000 tons and was removed intact rather than dismantled offshore. The objective was straightforward in principle: transport the entire upper structure to shore for dismantling and recycling. Achieving that objective required a vessel designed around the lifting task itself. The most recognizable feature was the split bow. Instead of approaching from the side like a conventional crane vessel, the ship moved forward until the platform stood between its twin hulls. This arrangement allowed lifting equipment to engage beneath the topside. The geometry reduced dependence on extremely large crane hooks and enabled direct load transfer into the vessel.
Approach operations demanded precision.
Dynamic positioning systems continuously controlled thrusters to maintain location and heading. Ballast systems adjusted draft and trim. Operators monitored environmental conditions and vessel response while moving into position. The platform remained fixed to its support structure, yet the vessel still experienced ocean motion. Managing that difference was central to the entire operation. Lifting beams were positioned beneath designated support areas. Motion compensation technology minimized relative movement between the vessel and the structure during engagement. The goal was not to eliminate ocean motion completely. Instead, it was to control the interaction so connections could be made safely and loads could be transferred according to plan. Separation work formed another essential stage. Structural connections joining the topside to its support structure had to be prepared and cut. Timing mattered because the topside needed to become free exactly when the lifting system was ready to accept weight. Premature release could create instability. Delayed release could interfere with the transfer sequence. Once engagement and separation were complete, hydraulic systems increased lifting force. Load gradually shifted away from the support structure and into the vessel. Engineers paid close attention to distribution. A structure weighing many thousands of tons cannot be treated as a single point load. Forces travel through decks, modules, columns, and connection points. Uneven transfer can create stresses beyond those anticipated during design assessments.
The fast lift phase addressed that risk. By completing separation rapidly, the operation reduced the window during which waves could generate unfavorable relative movement. Within seconds, the topside cleared its supports and rested securely on the vessel. What appeared from a distance to be a simple upward motion represented the coordination of marine control systems, structural engineering, hydraulics, ballast management, and operational planning. The achievement attracted attention because it established a lifting record at the time. Yet the significance extended beyond a single number. It demonstrated that very large offshore structures could be removed intact and transported to shore without extensive offshore dismantling campaigns. That concept altered expectations across the decommissioning sector. After the lift, transportation became the next priority. The topside remained secured aboard the vessel for the journey toward shore. The objective was not merely to move cargo from one location to another. Engineers had to preserve structural integrity throughout transit while accounting for vessel motions, weather conditions, and support arrangements. Arrival near the dismantling area introduced another transfer stage. Because of draft and access considerations, additional marine assets assisted with delivery. The structure could then be positioned for onshore processing, where dismantling activities were easier to control than in an offshore environment.
Recycling targets highlighted the broader purpose behind the operation. Large quantities of steel and other materials could be recovered once the topside reached land. Moving the structure intact concentrated cutting, sorting, and waste handling activities in a location designed for those tasks. The Brent Delta campaign also provided valuable experience. Engineers studied performance data, operational procedures, connection details, and preparation requirements. Later projects benefited from those lessons. Offshore work could be streamlined, preparation methods refined, and installation of temporary components reduced where appropriate. Viewed from shore, the removal may seem defined by a brief lifting sequence. In reality, the visible moment depended on years of design development, planning reviews, structural analysis, marine simulation, fabrication, testing, and operational coordination. The lift succeeded because every stage before it prepared the structure, vessel, and crew for a controlled transfer of an immense load from a fixed offshore platform onto a ship moving within an active sea. One reason the operation remains important is that it answered a question that had challenged decommissioning planners for years. Traditional removal strategies often relied on breaking structures into many sections offshore. Each additional lift introduced extra marine campaigns, vessel time, personnel exposure, and weather dependency. The single lift concept sought to compress those activities into a shorter offshore window while shifting dismantling work to shore. That approach required confidence in both the vessel and the structure. Engineers examined load cases covering engagement, transfer, lifting, transport, and support conditions. They evaluated how forces would move through the topside once it no longer rested on its original supports. Temporary strengthening measures could then be applied where necessary. Operational coordination was equally important. Marine crews, lifting specialists, ballast operators, survey teams, and control room personnel all worked from a common sequence. Decisions made by one group influenced the others. Maintaining communication reduced the chance of unexpected load shifts or positioning errors during critical stages. For the wider offshore industry, Brent Delta demonstrated that scale alone did not prevent removal. With the correct vessel architecture, controlled motion compensation, accurate positioning, and carefully managed load transfer, structures could reach shore safely.
The topside is gone, but beneath the waterline, the steel skeleton that held it up for decades is still standing in the seabed, and getting it out may be the harder job. A jacket for an offshore grid connection is towed to its location, roughly 130 kilometers off the German coast. The structure is upended from horizontal to vertical in open water, then lowered until it stands on the seabed. From that moment, every wave, every current, and every ton of topside it carries locks it deeper into the bottom.
The reason a jacket grips the seabed is not the weight of the steel. It is the piles driven through it. During original installation, long steel piles are threaded down through sleeves in each jacket leg, welded section by section as they grow deeper, and driven into the seabed soil by a hydraulic offshore pile hammer. Those piles anchor the structure to the bottom for the next 30 years. At end of life, every one of those anchor points has to be cut underwater before the jacket can move.
Before a single cut is made on a jacket leg, the steel around the cut line has to be found first. And after 30 years underwater, finding it means stripping away everything the sea has added. A subsea cleaning tool deployed from an ROV starts work on a section of structure covered in years of soft coral, biological deposit, and calcareous growth. The spinning brush head is brought up against the fouled surface by the ROV manipulator arm, and the growth strips away in seconds, exposing the steel joint underneath. The ROV operator drives the tool into the tight corners where jacket members meet, pressing it against the tubular intersections at the base of the structure where deposits build up heaviest. A second attachment, built for harder fouling, works on a length of pipeline running across the seabed. The brush head bites into the calcareous layer, releasing clouds of debris into the surrounding water as it advances along the line. After a few passes, the steel pipe is exposed again, clean enough for inspection of weld lines and corrosion pits underneath. The tool tracks along the axis of the pipe, methodical and continuous, working a length of subsea steel that no diver could clear in comparable time. On the jacket joints, the rotation is repeated until the surface is back to bare metal, ready for non-destructive testing or for marking the next cut. The geometry the tool handles is the geometry a jacket presents: large diameter tubulars, braces joining at nodes, pile sleeves, conductor guides, and riser clamps, all buried under marine growth that hides both the steel and whatever corrosion has been developing behind it. Mooring chain connections, pipeline tie-ends, and riser bases all need to be confirmed before disconnection. Every one of these surfaces has to be cleaned before an engineer can read the steel, and every one of them has to be read before the cutting plan can be finalized and the jacket can be freed from the seabed.
2 years of planning come down to a single sequence. Cut the legs, lift the skeleton, and get it onto the deck before the weather window closes. The Ninian Northern Jacket Removal is the first commercial deployment of a dedicated jacket lift system and one of the heaviest offshore jacket lifts ever performed. The jacket weighed approximately 8,100 tons and stood 85 meters tall in the northern North Sea, 160 kilometers northeast of the Shetland Islands. Its topsides had already been removed in a separate single-lift operation 2 years earlier, weighing 14,200 tons. The factory gone, the skeleton remained. 8 steel legs driven into the seabed by piles, braces running between them, risers and conductors still attached, and decades of marine growth and corrosion layered over everything below the waterline. What remains after topside removal often looks simpler, but the jacket still contains some of the most difficult structural challenges in offshore decommissioning. The lift vessel arrived in the Ninian field. The jacket lift system at the stern of the vessel consists of 2 connected beams, each 170 meters long, designed to lift and support jackets of all sizes during removal and installation.
The system is fundamentally different from conventional crane vessels. Instead of hoisting a load from a single point, the two beams work together to cradle the jacket along its full height, which means the structure can be transported in a near-vertical position, safeguarding its integrity during transit and eliminating the need for sea fastening. Supporting the structure along its height reduces concentrated stresses that would otherwise build up around a limited number of lifting points.
The beams were upended into their working position as the vessel approached the jacket. Main hoist blocks suspended from the beams were lowered and attached to the top of the jacket using bespoke rigging fabricated specifically for this lift. With the connections confirmed, underwater operations began. The 8 jacket legs had to be cut through below the mudline to separate the structure from the piles that had held it in the seabed for decades. Each cut had to be completed cleanly because an incomplete cut leaves the jacket partially attached, and a partial attachment under load is where uncontrolled failure starts. Engineers continuously verify cutting progress because even a small remaining steel connection can alter load distribution during the lift. Once all 8 legs were free, the jacket lift system engaged. The 85-meter structure was pulled clear of the water in a controlled lift, rising vertically out of the sea with the 2 beams holding it from both sides. With the jacket fully clear, it was aligned with the beams and tilted back onto the main aft deck of the vessel for transit. The system's capacity is rated at 20,000 tons for a single jacket lift, which means the 8,100-ton Ninian Northern jacket sat well inside the working envelope. The vessel then transported the jacket directly to the deepwater port of Lerwick in the Shetland Islands. At Lerwick, the jacket was transferred onto the cargo barge Iron Lady. The barge was maneuvered alongside the quay, and the jacket was skidded from the barge onto the quayside, where it was set down on concrete supports. From there, it would be delivered to a recycling yard targeting 98% steel reuse. The entire operation concluded 2 years of planning and design. In the same year, the vessel was committed to lifting and transporting more than 123,000 tons of offshore structures using both its jacket lift and its motion-compensated topsides lift systems. The jacket removal is the stage most viewers never think about. The topside gets the footage, the jacket gets the harder engineering. Cut it free from a seabed that has been gripping it for decades, lift an 85-meter steel frame out of the water without letting it twist or buckle, transport it hundreds of kilometers at near vertical, and land it on a quay intact enough for recycling. Every one of those steps depends on the underwater work that came before it.
When a jacket or a deck is still standing, engineers can plan around it. When it is already collapsed onto the seabed, the plan has to start from scratch, and the tools change completely. A pair of massive steel grappling devices were engineered, fabricated, tested, and deployed in a span of just 8 months, prompted by an offshore operator looking for a way to retrieve sunken platform topsides from the seabed while keeping divers out of the operation. Each unit measures 122 feet tall and 112 feet wide and weighs 1,000 tons. The fabrication footage shows the scale of the build. Large diameter tubulars are cut, welded, and joined into the curved jaw frames in a fabrication yard. Heavy cranes then assemble the 2 white jaw structures and the yellow hydraulic connection block at the top, placing the completed system onto a transport barge. Testing follows immediately. The claw is mounted on the heavy lift system aboard a work barge, lowered into the water, and closed around a test structure to verify hydraulic pressure, cable balance, and jaw alignment before any live deployment. A 3D animation then shows how the system works on the seabed. The claw is lowered from the surface with its jaws open wide. It descends around the target structure, closes its grip, and lifts the entire load without any diver having to attach rigging to the wreckage. This is the key difference from conventional subsea salvage. A standing jacket can be rigged with hoist blocks and bespoke connections designed months in advance. A collapsed structure on the seabed cannot. The geometry is unknown, the steel may be twisted, and sending divers into a debris field to attach lifting slings is one of the highest risk operations in the offshore industry. The claw eliminates that step entirely. Custom-engineered cradles were built to work with the claw. The cradles are lowered to the seabed next to the sunken platform deck, where they serve as a base.
The claw scoops up the damaged topside, deposits it onto the cradle, and the entire package, cradle and load together, is brought to the surface as one unit, placing no further bending stress on the fragile structure during the lift. The cradles were designed with flexibility built in, capable of being lifted either by the claw itself or by a separate rigging setup using two specially designed pipes. In the first live deployment, underwater camera footage from an ROV shows the claw descending through a debris field with fish swimming around the wreckage, closing its jaws around a sunken deck frame and lifting the entire structure clear of the seabed. The heavy lift system then brings the load to the surface and deposits it onto the transport barge. The campaign recovered 5 decks in 3 days. The system received an Industry Technology Award in 2012 for its contribution to reducing diver exposure during offshore salvage operations.
A 25,000-ton topside has just crossed from ocean to quay. From here, it stops being a platform and starts becoming material, and the first tools to touch it are the ones that cut it apart. A turret bearing, pulled from an FPSO during a refit, shows the scale of what has to be broken down on shore. The bearing is only 10 years old, made of carbon steel with heat-treated rollers and an Inconel overlay on the ceiling face, but clearance measurements showed it could not be guaranteed for the next deployment. A new bearing was ordered, and the old one sent for disposal. Workers in full protective gear feed a thermal lance into the structure, an iron conduit packed with steel rods and fed with pressurized oxygen. An oxyacetylene torch ignites the tip, and the oxygen sustains a reaction that burns at up to 4,000 degrees Celsius, hot enough to melt through heavy carbon steel in seconds. Molten metal runs out of the cut line as the lance advances. The bearing, once a precision-engineered part worth $2 million, is reduced to scrap sections ready for the furnace.
Once the heavy cutting is done, the scrap leaves the decommissioning quay and enters the recycling chain, and the recycling chain has its own engineering. A full-service scrap metal recycling facility receiving material from across the region shows how the sorting works in practice. Inbound trucks report to a scale where pictures of both unprocessed and processed material are recorded for traceability. A material inspector checks every load for quality, grading, and nonconformities, and a posted list of restricted and hazardous materials ensures nothing dangerous enters the operation. Obsolete metal items are processed through a large shredder that separates ferrous from non-ferrous metal mechanically. The non-ferrous product moves inside to a dedicated separation system that splits the material into 3 size fractions. Each fraction then passes over an eddy current separator, which uses a rotating magnetic field to eject non-ferrous metals from the non-metallic residue. The finished products that come off the line include shredded aluminum, shredded stainless steel, and a non-metallic product. An aspiration unit and water sprays throughout the shredder, and downstream equipment control dust and debris both inside the facility and around the surrounding area. Larger structural steel items that cannot fit through the shredder are processed through a vertical shear, which cuts unprepared material down to specifications that steel mills can accept directly. The recycled metal is marketed directly into steel mills and other end users to be used in the production of new raw.
How does a steel beam that spent 40 years holding up an oil platform become part of a new structure? The answer is a furnace, a mold, and a casting line that turns scrap back into certified raw material. A recently installed full scrap metal recycling plant shows the complete melting and casting sequence in one operation. The line begins with a 4-ton capacity mobile vibratory charging machine that feeds sorted scrap metal into a 15-ton tilt rotary furnace fired by oxy-fuel burners. The rotary furnace melts the incoming scrap at high temperature, while the rotation keeps the melt circulating evenly, reducing cold spots and ensuring consistent chemistry across the batch. Molten metal is then transferred to a 15-ton lip-axis side-tilting holding furnace equipped with a porous plug gas injection system. The gas injection stirs the melt from below, bringing dissolved impurities to the surface where they can be skimmed off, and the holding furnace keeps the metal at a controlled temperature until the casting line is ready to receive it. From the holding furnace, the molten metal is poured into a 220 mold ingot casting machine with indirect water cooling. The molds fill in sequence as the casting wheel rotates, and each ingot solidifies under controlled conditions so the cooling rate stays within specification. As the finished ingots come off the casting line, a robot ingot stacking system picks them up, quenches them in a cooling bath, and stacks them automatically for dispatch. The entire plant operates under an air pollution control system with continuous emission monitoring, so the exhaust from the furnaces is scrubbed and tracked in real time. The output of a line like this is certified ingot, a raw material that can re-enter the industrial supply chain as feedstock for foundries, rolling mills, or fabrication shops. For the steel coming off a decommissioned offshore platform, this is where the recycling percentage is finally locked in. Every ton of platform steel that reaches a furnace like this and comes out as a clean ingot counts toward the 97 or 98% recycling target the decommissioning industry has set for itself.
Steel makes up the bulk of an offshore platform, but buried inside the modules are thousands of valves, fittings, and instruments made of brass, bronze, copper, and stainless, and every one of those has its own recycling path. A vertical hammer shredder line demonstrates how a scrapyard recovers pure brass from a mixed non-ferrous feed. A crane with a grab bucket loads mixed scrap, old valves, pipe fittings, and hardware into the feed hopper of a conveyor. The conveyor carries the material up and into the vertical hammer shredder, which breaks it into uniform fragments. The shredded output passes over a magnetic drum that pulls out any ferrous content. The remaining non-ferrous mix continues through a sizing screen to remove dust and fine non-metallic waste, then passes over an eddy current separator that ejects the non-ferrous metal from any remaining non-metallic residue. The final output collected at the end of the line is clean brass fragments, separated to high purity and ready for melting. On a decommissioned platform, brass and bronze components are sorted out during the module teardown phase and fed into exactly this kind of downstream separation line, where they re-enter the non-ferrous supply chain as recovered metal rather than waste.
Every platform in this video followed the same path: shutdown, clean, cut, lift, transport, dismantle, recycle. The engineering behind each stage was precise, expensive, and years in the making. But the question the industry still has not settled is whether every platform should take that path at all. Full removal is the cleanest outcome on paper. The wells are plugged. The topside and jacket come out. The seabed is surveyed and verified clear. The steel goes to a yard where 97 or 98% of it re-enters the supply chain as recycled material. The ocean gets its patch of water back. But full removal is also the most expensive option, running into hundreds of millions of dollars for a single large platform. And the cost falls on the operator, the license partners, and in some jurisdictions, ultimately on the taxpayer. The North Sea alone faces a decommissioning bill estimated at around £24 billion over the decade to 2032, and that number has already been revised upward by roughly £3 billion since earlier forecasts. Partial reuse offers a different calculation. Some jackets and subsea structures can be repurposed as foundations for offshore wind turbines, as support frames for marine monitoring equipment, or as cable protection infrastructure. Reusing what exists avoids the cost and the carbon footprint of both removal and replacement. But reuse depends on location, on structural condition, and on whether the regulatory framework allows a structure built for oil and gas to serve a second life in a different industry.
In some parts of the world, decommissioned jackets are cut at a safe depth below the surface and left standing on the seabed, where they become artificial reef structures. The ecological argument is real, and in warm water regions, the results have been documented over decades. But a reef is also a permanent commitment. The steel will corrode, the coatings will degrade, and the decision to leave a structure in the sea means accepting responsibility for monitoring it long after the operator has moved on. Each of these options carries a cost, a risk, and a long-term consequence that outlasts the platform itself. Full removal is expensive and energy-intensive, but leaves the seabed clear. Reuse saves money and material, but depends on finding a second use that fits. Reef conversion supports marine ecology, but locks the liability into the seabed for generations. The honest answer is that no single option is correct for every platform. The geology, the water depth, the structural condition, the surrounding marine environment, the regulatory regime, and the available recycling infrastructure all shape the decision. Building these structures was one half of the offshore engineering challenge. Taking them apart safely, honestly, and with full accountability for what they leave behind is the other half. And that half is just getting started. After seeing what it takes to remove and recycle an offshore platform, what do you think should happen to old platforms? Full removal, partial reuse, or turning some of them into artificial reefs?
End of the line for this one. Follow along for more deep looks at the machines behind mining, farming, and manufacturing.